So thanks to Raghavan for the nice introduction. Can everyone hear me? So volume. Okay, so I'm going to use the board. So I'm just a little concerned that people who are probably seated right there may not quite be able to see everything I write. So maybe you can tell me if you can see me right now. Yeah, you I'm sure can, but people there? Last row? No? Talk about today. It's called partitions, and so the easiest way to really begin is just by writing out an example. We don't quite need to say too much about this. So let me just say what a partition is by example. So the starting point is natural number. So you start with a number, for example 4, and then you partition it. Okay? So what the English word partition means is exactly what we will do. We will try and write 4 in all possible ways as a sum of natural numbers. Okay, am I missing any? Okay, so 2 plus 1 plus 1. Am I missing any more? Is there any other way of writing 4 as a sum of other numbers? Right, minus 1 plus dot dot dot. So I want, the condition is I don't want to have 0 or negative numbers involved. Okay, I only want to write it as a sum of positive numbers, positive integers, which means this is pretty much it. I can't really decompose it in any further way, right? So these are all the partitions of 4. What I have done is written out all the partitions of 4. So since we have done 4, let's do somewhat smaller example, 3. What are the partitions of 3? So there are 3 of them. Okay. 2. That's it, right? So what we are interested in for a start is to see how many total partitions there are for a given number. Okay. So to do this, we will sort of introduce a function. Let's call it P of n. So n is this number we start with. P of n will denote the number of partitions, the total number of partitions of n. Okay, so let's make a table, maybe here. So we already have some numbers, 2, 3, 4. So what do I put here? What's P of 2? P of 3? Right? There are 5 partitions of 4, 3 of 3 and 2 of 2. What's P of 1? There's only one partition, which is 1 itself, right? Okay, so maybe 30 seconds to find P of 5. What's P of 5? 8. Any other answers? We'll sort of get there by successive approximation. I have 8. Anyone wants to disagree? What do you have? 7. Any other numbers? Any other numbers? I'm going to hand it to the 7s if I don't hear. Okay, it's 7. So the ones who got 8, for example, why did you get 8? So firstly, how did you find this? You wrote all partitions out, I suppose, right? Those who said P of 5 is 8, for example, or those who said it's 7 even, what you probably did is to write all partitions out. So those who wrote out, who said it's 8, so can you maybe look at your list and see if you're finding a repetition? I forget who said 8. Anyone who said 8? Okay, so if you look at your list, what you will find is the following. So there's nothing wrong in saying 8, by the way. So meaning it's rather difficult and subtle to try and write out a complete list of all partitions without involving repetitions. Okay, so what you will find often is that one of the standard things is you might have taken the same things in a different order. Okay, 5 for example is I don't know, 3 plus 2, maybe you also counted 2 plus 3 as a possibility. Okay, so I don't want to think of 3 plus 2 and 2 plus 3 as two different things. They are the same partition really, right? I must take 1 3 and 1 2 in order to partition 5. Okay, so let's do one more. This time I'll write all the partitions out. So I'm going to find P of 6. I probably need some more space to, so let's, okay, so NPN. So let me just write all the partitions of 6 out. 6. So maybe you can just shout out the partitions. 5 plus 1. Any more which involve 4? Okay, 4 plus 1 plus 1. 3 plus. Okay, so how many did we get? 1, 2, 3, 4, 5, 6, 7. One, 1, 2 and all ones, and then 6 ones, right? So observe there's sort of a method in the way we wrote it out. You try and, so firstly it's customary to write partitions in decreasing order. Because we don't care for order, let's choose to write all partitions in decreasing order. So I start with the largest and keep going down. Now what you do is you pick a part, say the largest part is 5, and then there's only one possibility, 1. Then you go down, you change this to 4, and then you see what all possibilities are there for the other guy. So here it's 2 for a start, and then you decrease the 2, make it a 1 and see what you can get. Then you go, there's nothing further in this direction, then you go down to a 3, take the largest possibility for the next part, 3 again, and sort of work through systematically. If you do this, you will find you won't get any repetitions. This is probably the best way or systematic way of finding the number of partitions. So what's P of 6? Okay, so P of 6 is 11. So Professor Ramanujam talked about exploratory projects. Partitions is actually a fantastic world where you have tons and tons of exploratory things you can do on your own. For example, the simplest thing to do is find out what it is for the next few values. Okay, and you will find that it already gets somewhat harder to do this. So P of 10 is already somewhat large. Okay, and if you sort of keep going down, you will find, for example, that P of 200 is probably not something you can do by hand. Okay, I mean it gets out of hand even much before that. But P of 200 is an insanely large number. Okay, it's already a very, very large number. And so the partition function in fact grows. It grows extremely fast. Okay, it sort of has this exponential growth. So there are a few more things that I probably want to say about this, but I'll come back to it at the end of the talk again. You probably, if you read my abstract, you noted there were many famous mathematicians who have contributed to this theory. So you can see it's actually the simplest possible thing you might want to do, right? I mean, you can spend several summer afternoons doing this by yourself. And so needless to say, several mathematicians did this from, starting from Euler, who was one of the very famous mathematicians in the 1700s. And then, there's a lull for a while. Euler proved several wonderful results. And then, sort of in the late 18th century, late 19th century, there were some English mathematicians, Sylvester and Rogers and so on. And then none other than Ramanujan himself, together with Hardy in the 1910s and so on, proved some spectacular results about P of n. Okay? And it was sort of followed again by a whole century of several more results. culminating with, maybe not culminating, still it's an ongoing process. There's another spectacular breakthrough in 2011, which is just 2 years ago. So it's very much an alive and kicking field, meaning it's such a simple concept, but it continues to excite mathematicians and continues to produce very interesting results, and with very deep connections to many other parts of maths and physics, in fact. Okay, so what I want to focus on, however, is some special kinds of partitions. Okay, so counting all partitions is already making this list is a big task. Let's sort of make the problem a little simpler. So let's say I want to talk about special partitions which have some additional properties. Okay, special types of partitions. So maybe I should say special types. So I'll name a few. So let me start with the first type, which I'll call A. So here's a condition. So I'm going to say something more. I only want to take partitions in which every part is less than or equal to 3. Okay, so I'm putting an additional restriction. I want the parts. By parts, of course, we mean these numbers which occur here. We want them to be at most 3. Okay, so that's the first restriction that I want to put. Okay, so let's try and enumerate this. This is a simpler problem, of course. Let's try and list this out for, let's say, n equal to 6. Okay, so I'll take n equal to 6. And let me only list those partitions of this type, I'll call it type A. So this is only partitions of type A. Okay, so let's go through the list, throw out the ones which don't satisfy this property. So what ones do I get? What's the very first one I get? 3 plus 3, followed by? Well, in fact, everything after it in my list. And all ones. Okay, so that's a full list. How many do we have? 1, 2, 3, 4, 5, 6, 7 of them. Okay, so there are 7 partitions of 6 in which every part is at most 3. Now I want to talk about another type, type B. So which I'll also enumerate here. So type B. But I should tell you what type B means. So here's type B, partitions in which the number of parts so this is a somewhat different notion here. Right? By number of parts, you understand what I mean? For example, how many parts does this partition have? 4, right? It's 3, and then there are 3 ones. So it is 4 parts totally. The number of parts should be at most 3. Okay? That's my new condition. So let's write out type B. Which of these satisfy type B? 6 is okay. Three plus any more? That's it, right? That's a full list. Only 3, maximum 3 parts allowed. All the rest have 4 or more parts. How many do I have? 7. Okay. Of course, I sort of rigged the example, or I sort of gave you something for which I know the answer. What do you think is true? These two are always the same. Okay, no matter what n I pick, if you take n equals 200 if you wish, and you write out all partitions of type A, then it will be some list. The partitions of type B will be another list. I don't know how many numbers there are, I don't know how many partitions of each type there are, but I can say for sure that the number of partitions of type A is exactly equal to the number of partitions of type B. Okay? So that's the theorem or statement. So here's a statement, so we'll call it theorem if you wish. For every n, not just for n equal to 6, for every n, every natural number n, let's sort of be lazy and say number of partitions of n of type A. So I will use this notation to say it's number of partitions of n with the additional property that it satisfies type A equals, maybe I'll put A with the circle, is number of partitions of n which satisfies type B, which is of type B. Okay, for n equal to 6, of course, it is 7, both are 7. Okay, so we'll soon see why this is true. Does anyone offhand have an idea why this might be true? Okay, good. So we'll do this in just a second. So I'll get rid of this. So let's leave this aside for a moment and talk about something which will soon be seen to have a bearing on this. I'm going to start drawing diagrams. Okay, so I'll call something a diagram of a partition. Okay, so again, there's no sense in formally defining it. We'll just do it by example, and it'll become absolutely clear what it means. Let me draw the diagram of the partition 3 plus 3 plus, so I'll take a partition 3 plus 3 plus 2 plus 2 plus 1. Suppose this is my partition. What is it the partition of? 6, 10, 11. It's a partition of 11, some partition of 11. I'll tell you what I mean by the diagram of this partition. Okay, so let's do the following. The first part is a 3, so I'll draw 3 boxes. Okay, so that's 3. The next is also a 3, so I'll draw 3 more boxes in the second row, 2 boxes in the third row, 2 in the fourth row, and a 1 in the fifth row. Fine? So it's clear what I mean by the diagram, right? You draw as many boxes. This is the box diagram. I draw as many boxes as there are parts, and I keep going down row by row. So that's a diagram of this partition. Okay, now when I have a diagram, I also have, well, let me do the following. When I have a diagram, I'll sort of also draw this bounding rectangle. So I'll just complete this shape. Think of this like it's sitting inside this rectangle. The rectangle has a height and a width. Okay, so let's say this is the height of the rectangle, height h, and width w. That's the width and height of the bounding box, if you wish. Okay, so that's the rectangle inside which my diagram sits. Now, here's what I want to do. What does type A mean in terms of the diagram? Okay, type A, this is the definition, partitions in which every part is at most 3, right? Now I want to rephrase this in terms of my diagram. Okay, so I'm going to sort of, let's say, complete the sentence. Partitions whose diagram has width at most 3, right? Because every part is at most 3, and what does it mean? If everything is 3 or less, the width can be at most 3, because the width is really the same as the number of boxes in the first part, right? The largest part is exactly the width. So in partitions whose diagram has width at most 3. Okay, and what about type 2? Partitions in which the number of parts is exactly the height, right? It's exactly the height, in fact, because here it's 1, 2, 3, 4, there are 5 parts, which means there are 5 boxes in the first column. So the height is exactly the number of parts. So we rephrase this in which the whose diagram partitions whose diagram has height at most 3 . Okay, so this is the diagrammatic interpretation of what A and B mean. Now let's go back and see if we can now, if this sheds more light on our theorem. We are saying the number of partitions of type A and type B are the same. Okay, is there an operation which will convert a partition of type A into a partition of type B? What should you do? Okay, does that have a name? Have you ever seen it in any other context? Transpose, absolutely, right? So basically the operation is the following. One of them has width at most 3, the other has height at most 3. So what you must do is really transpose the partition, right? Which means you sort of rotate it by 90 degrees, and then when you rotate, of course, it's not quite left justified. So then you push the boxes so that it starts at the top left corner. Okay, in other words, you take the transpose of the partition. So what does transpose mean? Let's do it by example again. So what is transpose? So what's the transpose partition or the transpose diagram? Okay, it's really a diagrammatic notion, transpose partition or diagram. So let's do it here. It's 3, 3, 2, 2, 1. Transpose basically means you take the first column and think of it as the first row. So first column is 5, second column is 4, third column is 2. So now think of a new partition which is 5, 4, 2. Okay, so I'll draw the box. 1, 2, 3, 4, 5. Right? So how did I get that from here? I just transposed the diagram. So this is the transpose. This is fine. Any questions on what transpose means? Because that's sort of the important point here. Instead of reading the partition along the rows, you read it along the columns. That's another way of saying it. Okay? Or alternately, you take the original diagram and you interchange the role of the height and the width. In other words, you reflect about the diagonal. Okay, you push it across, you reflect the whole thing across this diagonal. So has everyone seen matrices and so on? I expect maybe not everyone, right? Matrix? Matrix? Anyone who's not seen matrices before? Everyone sees matrices. Okay, I'm sure there are at least people in 11th probably haven't seen matrices before. A matrix is essentially a rectangular gadget where you sort of do the same thing, you reflect about the diagonal. This is not quite rectangular, meaning some boxes are missing, but the same idea works. Okay, so this is the transpose partition, which is 5 plus 4 plus 2. Okay. So now here's what I want to do. So here's the claim. I mean, it's visually obvious now. If you take a partition of type A and you transpose it, what you get is a partition of type B, right? So let's actually see it here. So I want to take each of these and I want to do transpose to them. And let's see what you get on the other side. Okay, so I'm going to apply transpose. What is 3 plus 3 transpose? 3 plus 3? 2 plus 2 plus 2, right? Let's just do 1 or 2 on the board. So here's 3 plus 3 looks like this. Now I should read it along the columns, 2 plus 2 plus 2. So that's this. Transpose of this fellow is that fellow. What's the transpose of 3 plus 2 plus 1? It's itself, right? So this is sometimes what's called a symmetric partition, like sort of in analogy with symmetric matrices, because it's somebody which is its own transpose. Transposing it doesn't change it. Okay, what is 3 plus 1 plus 1 plus 1? Sorry, I can't hear. What? 4 plus 1 plus 1? Okay. So I'm just going to trust you on this. 2 plus 2 plus 2? See, now here we have already done the work. We don't need to do it. If this transpose is that, then that transpose is this again. So if you do 2 transposes, you come back to the starting point, right? So no need to do work again. 2 plus 2 plus 2 is 3 plus 3. What is this? 2, 2, 1, 1. 4 plus? Four plus? You are doing this incredibly quickly. I wonder how do you do this? By actually writing out the diagram? Sort of just visually, is it? Okay, it takes me a long time to do this. Okay, what is 2 plus several ones? That's easy. Sorry, it looks like a horrible match the following thing, but that's the proof. The theorem is proved, right? Does everybody agree the theorem is proved? Right? We did it by example, but what we have done eventually is construct an operation which converts everything of the first type into something of the second type, right? And this operation is invertible, meaning you can apply it, it's also vice versa. If you apply it to something of type B, what you get is something of type A, right? It's its own inverse. If you do it twice, you get back the same thing. So there's a name for such things, right? So suppose you want more generally, this is in the context of partitions, but if you had 2 sets in general, so I'll draw some Venn diagrams and so on. I have 2 sets, and I want to show that number of elements in set A and the number of elements in set S and set T are the same. I want to show that the number of elements here and the number of elements there is the same. So imagine there is a set consisting of these 7 fellows, another set consisting of those 7 fellows. So what have I produced? Bijection, perfect. So that's the name for, what is a bijection? One-to-one onto map, right? What have we done? We have constructed a bijection between the partitions of type A and the partitions of type B. So what's a bijection? It's a one-to-one onto map between 2 sets. So often, what this does is the following. We don't know how many there are in general. If you ask me how many partitions there are of 200 of type A, I don't know the answer. But I can tell you that the number of partitions of type A of 200 is the same as the number of partitions of type B. Right? All I'm saying is these two have the same number, but what number that is, I don't know. I'm just claiming equality. Okay, so this is often called a bijective proof. What we have just done is a bijective proof of a partition identity. Okay, and these are often the very interesting and often difficult proofs to construct. Okay, this whole theory is full of, partitions is full of such identities, very, very interesting connections between things of type A and type B, where A and B can be various things. Okay, so I'm going to give you another example. So any questions, by the way, on any of this? Okay, and needless to say, I can change that 3 to any other number. So number of partitions, A was things in which every part is at most 3. I can change the 3 to any number D, right? Because it finally boils down to saying it's all those fellows whose width is at most D. Type B is things whose height is at most D. And D can be any number, it doesn't matter, you will still get the same answer. Okay, so I'm going to define partitions of 2 more types. So I'll call them types C and D now. So again, I will first say what they are, sort of in words, and then we'll convert it into diagrams. So here's the condition: difference between consecutive parts. So by consecutive, I mean I've arranged them in decreasing order. Difference between consecutive parts is at least 2. Okay, so if 6 is one of the parts, the one after it has to be 4 or less. I'm not allowed to take 6, 6 or 6, 5 as my numbers in a partition. Okay, difference should be at least 2 between 2 partitions. So what's an example? So let's do this again. Type C, and I need n to be somewhat large for this to make sense. So let me do n equals 9. Here's type C. I'll soon have type D. What are all the partitions of 9 which satisfy this condition, that difference between consecutive parts is at least 2. What's the very first one? 9 itself. 8 plus 1 is fine, difference is 7. 6 plus 3. 5 plus 4 allowed or not allowed? Not allowed because 5 and 4 differ only by 1, right? Difference should be at least 2. 5, 3, 1? Yes, that's allowed. Any more? 6, 2, 1 allowed or not allowed? 2 and 1, right? 2 and 1 differ by 1. So every consecutive pair should differ at least by 2. Okay, so that's it. That's the full list. There are only 5 of them. 9, 8 plus 1, 7 plus 2, 6 plus 3, 5 plus 3 plus 1. Okay, I leave space for the diagrammatic representation, which probably won't fit in this space, so forget it. So here's something very strange, something we have not, it's a flavor that we haven't seen before. Each part, every part in the partition has to be at least equal to the total number of parts. Okay, so we sort of have to wrap our heads around this. Let's do it by example. Let's do it, number of parts at a time. Suppose the partition has only one part. That part has to be 9, no other choice. Suppose it has 2 parts. 8 plus 1 okay or no? 8 plus 1 is not okay because 1 is smaller than 2, right? If I have 2 parts, both parts should be at least 2. 7 plus 2, 6 plus 3, 5 plus 4, 7 plus 2, 6 plus 3, 5 plus 4. Those are all okay. That's it, right? 2 parts, that's all. 3 parts. If I have 3 parts, 3 plus 3 plus 3 is the only option because if I have 3 parts, each of them must be at least 3. That's my condition, right? Each part is at least equal to the number of parts. So if I have 3 parts, then there's only one, 3 plus 3 plus 3. And there are no other choices. That's it. That's the full list. Okay. So what do you think is the theorem? For every n, the number of partitions of type C is the same as the number of partitions of type D. Okay, so here's another theorem. C and D always have the same number of parts. Okay, so again let's prove this. It looks even harder than the earlier one. Let us prove this by first seeing what it means in terms of the diagrams. Okay, so let's try and interpret the diagrams. Okay, so let's see what condition C means in terms of the diagram. What does it say? Difference between consecutive parts is at least 2, right? So here's what it means. So okay, there's some diagram. The diagram of the partition looks, I'll just draw the outline. Let's say it looks like this, right? Those are the boxes inside. The last part, so let me start from the bottom. The last part, how many boxes can there be? At least one, no? Can be more than one, of course. At least one. So the last thing is there's at least one box. Maybe there are more boxes, I don't know. It's possible. Okay, what about the part before it? This is at least 1, at least 3, because difference is at least 2, right? So if this is a 1, then this must be at least 3 boxes long. So let's draw that. 3 boxes. And maybe there's more, I don't know, that I leave out. 5 boxes, 4, 5 boxes, and then followed by something to the right, right? So that's the shape of this guy. You have, let's say this diagram has, this is height, right? Height h. So then I keep going like this. What's the last, how many boxes are there in this row? How many boxes? it's odd numbers, right? 1, 3, 5, 7 and so on. What is the hth odd number called? I mean, what is it? 2h minus 1. So the hth guy is 2h minus 1. That's the hth odd number. And of course, there could be things to the right. I'm not saying they can't. So there could be things to the right. Okay. So what does condition C mean? It says the following, that the diagram of your partition has an inscribed zigzag figure. So here's the zigzag figure inside your partition. It's this 3, 5, 7 and so on. So things which keep going like this, well, whatever, all the way till I get to this point. Okay. So sorry, it looks like a mess. So there is an inscribed figure like this with 1, 3, 5, 7, 2h minus 1 boxes, and things to the right of it. What can I say about things to the right of this figure? There are some boxes presumably to the right of this figure. Okay. So there's a bunch of boxes. I don't know what they look like, but what I can say for sure is, okay, so let's do it this way. Suppose let's look at 1 and 3. Let's look at the last two rows. How many boxes can there be to the right of this 1? So suppose there are some k boxes, let's say there are 3 boxes to the right of 1. Okay. How many boxes should there now be to the right of 3? Yeah? At least 3 boxes. Why? Difference is 2, right? The difference should be maintained. So if there are 3 boxes here, then at least 3 boxes should also be there above it. Only then the difference of 2 is going to be maintained. So now say let's say there are 7 boxes in the next row, or 6 boxes over here to the right of a 3, then this guy should also have 6 boxes. Okay. So what it means is the following, that if a partition is of type C, a type C partition, can be decomposed into two pieces. One is this inscribed zigzag figure, 1, 3, 5, 7, whatever. So that's the inscribed part. Okay. Plus stuff to the right, which is in itself a partition. Okay. The boxes to the right themselves form a partition of some other number. Okay. Because if there are, it's already in decreasing order still. If there are 3 boxes here, there are at least 3 boxes in the next row. Okay. So there's some stuff to the right which in itself forms a partition if you think of it separately. Okay. You cut it out and you rearrange those boxes, they will still be in decreasing order. That's what I mean. Okay. So type C partition is in fact the following. It admits there is an inscribed zigzag fellow followed by these boxes which in themselves form a partition. So comma partition of some number. Okay, it can be obtained by gluing these two pieces of information together. That's what a type C partition looks like. Questions? Okay, let's do type D. So what does type D mean? Each part is greater than or equal to number of parts. So what is number of parts in the diagram? The number of parts is exactly the height, right? So we just said this, the number of parts of the diagram is exactly the height of the diagram. So what we are saying is every part is at least equal to h. Okay, in particular the smallest part, the very last row, what is the size of the last row? At least h, right? It can be more than h, but surely at least h is there. Could be bigger than h also. There are at least h boxes. And so of course everything above it is also at least h. So in other words, something of type D has an inscribed square. It doesn't have an inscribed zigzag shape. What it has is an inscribed square. Okay, so there's a h cross h square, and things to the right of the square again form a partition of something. That's a partition here. Okay. So type D fellows again admit a similar description. Type D partitions can be cut into 2 parts. One, the inscribed square which you pull out, and what's to the right of the inscribed square is again some partition. comma partition of some number. Okay. So type C and type D, we have both of them here. So now here's the question. I want a bijective proof that number of partitions of type C is equal to those of type D, which means I want a way, an operation which will convert a type C partition into a type D partition. I give you a type C partition, I want a way of producing a type D partition from it. Can anyone see what needs to be done? Okay, let's do a small calculation that should give us a hint. How many boxes are there in the zigzag piece? H square. Why? Arithmetic progression. Sum of the first H odd numbers, right? 1 plus 3 plus 5 and so on is exactly H square. Okay, so here's an interesting fact which may be useful. Fact, remember the sum of the odd numbers is exactly H square. Okay, now I want a bijection. Absolutely. So here is an algorithm. So okay, what is the observation? The zigzag piece has exactly H square boxes. H square is the number of boxes in a square of side H. Right? So what should we do? What's the operation? You take a type C partition and you do the following. Okay, so let's write it out. Here's the algorithm. So here's an algorithm to convert type C into type D. Start with type C partition. Cut out the zigzag. The inscribed part. How many boxes it has? H square. Rearrange it into a square. Take those boxes out and form a square of side H. Into a square and keep the remaining as it is. Paste. So paste the remaining boxes as it is. Paste the remaining. Okay, keep the remaining unchanged. Whatever is to the right of the zigzag, you keep them to the right of the square. Okay, so key operation is only in converting the zigzag into a square. That's it. Okay, so let's do it to this guy and see what the match the following looks like. What do these become under this operation? Let's perform the algorithm. So I want to perform my algorithm to convert type C into type D. Okay, so let's do it one by one. There are only 5 of them. So let's take something which might be interesting. Let's say 6-3. I'll start with 6-3 and I see how to convert it. Let's take the partition 6 plus 3. That's type C, right? So this is a type C partition. So what does the diagram look like? 6, 1, 2, 3, 4, 5. Here is 6, 3. So what is the zigzag going to look like? How many boxes? 1 here and 3 there. That's my zigzag. This is it. This much is my zigzag portion. Okay, so I have 4 boxes total. So what should I do? I convert the zigzag into a 2 cross 2 square. Okay, so I cut this out and in its place I write a 2 cross 2 square of boxes. So I write a 2 cross 2 square now. And now I paste the remaining as it is. What do I mean by that? I have 3 boxes here, I'll paste 3 boxes here. I have 2 boxes here, I paste 2 boxes here. That's what I mean by the last step. Paste the remaining boxes as it is. This is what is meant. What's this partition? 1, 2, 5 plus 4. 6 plus 3 became 5 plus 4. Okay. So observe, 6 plus 3 is also in the other list, right? But 6 plus 3 didn't go to 6 plus 3. There's no reason for it to happen. Okay. What it does is there's some strange mysterious stuff going on which converts 6 plus 3 into 5 plus 4. So let's do the other ones. What? 7 plus 2. Okay, instead of 6 plus 3, if I had 7 plus 2, which means 7, one more box here, one less box here. This 2 cross 2 is the same, but I should have one more on top and one less on the bottom. What's that? 7 plus 2 became 6 plus 3. Okay, they're just coincidentally written right next to each other. 8 plus 1, it becomes 7 plus 2. 9 becomes, 9 remains 9 actually, because there's nothing to do, right? 9 is just one single long row. The zigzag is only one single box. This is it. It's supposed to be 1 plus 3 plus 5. It's just 1. So that 1 cross 1 box you make into a 1 cross 1 square and you paste the remaining 8 as it is. So 9 goes to 9. What about 5 plus 3 plus 1? That's the interesting fellow. It's clear what it must go to, but we will see how it works. So I have 5. 3, 1. So what's the zigzag here? The whole thing, right? The zigzag is the whole thing because it's exactly your definition of the zigzag. 1, 3, 5. So this whole fellow is my zigzag. There's nothing to the right of it, right? So I have 9 boxes in my zigzag. I convert it into a 3 cross 3 square. So first step, rearrange this into a square. Okay, done. And now paste the remaining boxes. There are no more boxes to paste. So you stop. What's that? 3 plus 3 plus 3. Right? So here's the algorithm. Here's the bijective proof that we were looking for, which shows that things which are, this is called minimum difference 2 between consecutive parts is the same as the number of partitions in which every part is at least equal to the number of parts. Okay? Now here's something, I'll write out one more type which cannot be so I'll write type E. Okay. You're not proving the what? You mean this algorithm, this one? No, okay. So that it's a bijection you mean, right? See, for the earlier example it's done. Do you agree? For the transpose, do you think that's rigorous? Yeah, because there if you do, to prove that some map is a bijection, what I should do is produce an inverse map also. There are 2 maps, one from this set to that set, one from the other set to this set, so that the composition is identity. Now the transpose is its own inverse. If you do it twice, you get back the same thing. Here for this algorithm, you need to do the same thing. You are right, I have not quite done it rigorously. I only gave you an algorithm which converts things of type C to type D, but I should give you a reverse algorithm as well. Okay, so this is the algo to go from C to D, but it's trivial to go from D to C by the same logic, right? There's a reverse algo. What's the reverse algo? Take the square, convert to zigzag, right? That's again a unique way of doing it. I mean, that's the algorithm, and clearly these two are inverse operations. Yes, absolutely. You need to show maps in both directions. If you do that, then of course it proves it's a bijection. So you are right, I didn't quite do the entire thing. I only give you the algo, but there is a reverse algo, which is take square, rearrange the square into a zigzag, and then paste the rest as it is. Yes, thanks. Okay, so now I am about to write out another type, another property, which is very, very unlike anything we have seen until now. So here's the condition. These are partitions in which each part Okay, I'm looking for partitions which have the property that each part has the last digit, units digit should be 1, 4, 6 or 9. Okay, which means I'm allowed to use 1, 4, 6, 9, 11, 14, 16, 19, 21, blah, blah, blah. But I'm only allowed to use those numbers. I'm not allowed to use any other numbers. Okay, only things which end in 1, 4, 6 or 9. Okay, so let's write those out. What are type E partitions of 9? How many partitions, well, what are they firstly? What are the type E partitions? Nine itself is fine. 6 plus, anything with 6? 1 plus 1 plus 1. Anything with 4? 4 plus? 4 plus all ones, then all ones. Right? I am allowed to use 1, 4, 6 or 9. This is all I can do. Okay, how many did I get? 5, right? Same as what I got in the earlier two cases. And this is completely, it's a very different ball game. It's actually true. Here's the theorem that in fact those of type E are also equal to those of type C and D. So this is a theorem. It says for every n, partitions of n into type E is also the same as partitions of n into type C or type D. Okay, all of these are the same. Okay, and this is a very famous theorem due to the English mathematician Rogers and Ramanujan. Okay, this is called the Rogers-Ramanujan theorem or the Rogers-Ramanujan identity. So the history of this goes that Ramanujan, when he arrived in Cambridge, so it was something that Ramanujan sort of discovered using his own methods without proof as usual, and Hardy was unable to prove it, and so were none of the other people, Littlewood, or there were several very famous mathematicians in Cambridge in the British mathematics at that time. None of them could actually give a proof. So there is a way of rewording this in terms of infinite series and so on, but none of them could actually prove it. So they sort of just accepted it, however, as something that surely must be true, because they calculated this up to, I think, n equals 89 or something. So they went up to n equals 89 and saw that these numbers were always the same until 89. And of course, Ramanujan sort of very definitively said it's true, and they checked it till 89. So they were very confident that it's true, but nobody could actually prove it. Okay, and so it so happened that Ramanujan himself, sitting in the Cambridge library, apparently looked at this journal proceedings of the London Mathematical Society or something, and found that it had actually been proved by an English mathematician called Rogers some 20 years before, in the 18 something, late 1800s, I think. And so then they dug out Rogers and sort of corresponded with him, and the two of them came up with another proof, a different proof than the one Rogers had initially given. Okay, so it's sort of the theory of partitions is full of lots of colorful anecdotes and stories involving the lives of the various mathematicians here. Now, so this is a very different ball game. So I just want to stress that this doesn't quite have a diagrammatic interpretation, unlike the earlier two things. You can't quite write this out. You can't quite describe this in terms of a diagram, right? It says that all parts are, either 1, 4, 6, or 9. Another way of saying this, if you have sort of seen these kinds of things before, is to say when you divide by 5, you get a remainder of 1, okay, or 4, plus or minus 1 when you divide by 5. Okay, so there is these various divisibility properties of involving congruences, as they are called, and there are hundreds of them. There are many such theorems which involve using parts which are congruent to, or whose remainders are some fixed numbers and so on and so forth. Okay, so Great, I have 5 minutes, so okay, something called infinite series, so which I'm not sure everyone has seen this before, but maybe at least some people who have seen arithmetic progressions and geometric progression. Somebody mentioned arithmetic progression. So if I take 1 plus x plus x square till x power n, is this something that you have seen before? 1 plus x square. What is this called? It's that the terms are in a geometric progression, right? And there is a way of summing up the terms of a geometric progression. What's the answer? A into r power. Okay, great. So I will substitute values of a and r and tell you what the answer is. It's this, right? Because you have to put a equals 1, that's the first term, r equals x, and you are used to probably seeing it as x power n plus 1 minus 1 by x minus 1. Okay, so I've just reordered the terms. Fine. So this is a geometric progression. Now it turns out you can actually forget about, instead of putting n to be some finite number, you just let n go to infinity, whatever that means. Okay, so sort of take whatever I'm saying with a small pinch of salt, but just let n go to infinity, which means you add all the terms of this series, infinitely many terms, and what do you get then? Okay, great. So you also seen that. Okay, so the answer is this. It's 1 over 1 minus x in this case. A by 1 minus r, as somebody just said. This is what's called the sum of a convergent geometric progression. Okay, but whatever, if you are willing to accept this, there's a very nice connection of this with partitions. Okay, so let me just tell you what that looks like. So we have taken this for granted. Now I'll do the following. I will write out this infinite series. I'll write it like this. 2 I will write as 1 plus 1. 3 is 1 plus 1 plus 1, and so on. Keep going like that. Okay, here's a geometric progression. What's the value? 1 over 1 minus x. Okay, I'll write one more. I write the same thing, but with x replaced by x square. I'll write one more with x replaced by x cubed. And so on. Okay, I've written 3 of them. What are the values? This is 1 over 1 minus x. The second guy, 1 over 1 minus x square, because I just done the same thing, but x square plays the role of x, that's all. Third one is x cubed, and so on. Okay, now what I'm going to do here is also take all numbers. I'm going to write an infinite product. Okay, whatever that means, ignore such matters for the moment. So here's a thing that I've written out. Now here's what I want to do. Just imagine you're doing polynomials, right? I have to multiply a bunch of polynomials, blah blah blah. Okay, so in this entire mess, in this big series that I have, suppose I want to find the coefficient of x power 4. I want to find in this infinite product, I want to somehow figure out what is the coefficient of x power 4. So I'm going to ask, let me find coefficient of x power 4. Okay, so it's a little combinatorial thing. We have to figure out how can you get x power 4 from this whole mess, right? So what should I do? I should either pick x power 4 from here, x power 1 plus 1 plus 1 plus 1, right? That's an x power 4. What are the other possibilities? X power 2 plus 2, x power 2 times x power 1 plus 1, right? X power 1 times x power 3 and x power 4. So how can I get x power 4? It comes in the following ways. One, I can just pull out x power 4 from that term. I can pull out x power 3 times x power 1, x power 2 plus 2, x power 2 times x power 1 plus 1 or x power 1 plus 1 plus 1 plus 1. So what's the coefficient of x power 4? Not 1, it comes in 5 different ways, that's what it means, right? See, I can get it in 5 different ways. That same term will come in 5 ways. So the coefficient is 5, right? What's the coefficient of x power 6? Why? No. Okay, partition is the correct answer. How many partitions were there of 6? 11, right? But in general, it's clear, right? What's happening? You can already see the partitions of 4 arising in this expression here. So the more general thing, what's the coefficient of x power n is exactly the partitions of n. Okay. So here's a way of getting the partitions of n by playing around with polynomials or series. You write out all those guys, and if you try and collect one single coefficient x power n, it's exactly p of n. Okay. And this is in fact the original method that Euler sort of introduced and used to great effect. It's called the method of generating functions. Okay, I'm already a couple of minutes ahead, I'll stop.